Hello students, welcome to the part 3 of our chapter Electromagnetic Induction. Today we are going to first discuss the EMF induced in a coil when it is rotating inside a uniform magnetic field. So here in the picture we are observing a coil PQ which is initially held in the uniform magnetic field such that the normal to the surface of the coil is initially pointing in the direction of the magnetic field as it is shown by the red arrow. If we assume that this coil is rotating with a uniform angular velocity omega, then during it will be rotation, suppose it turns an angle in a small time t, that angle theta it will be equal to omega into t using the definition of angular velocity. Now, when the coil turns in the clockwise direction by an angle theta, then the normal to the surface of the coil will also turn by the same angle theta in this direction. So, in this case, when the coil is rotating, the magnetic flux passing through the coil is continuously changing with time and it is going to induce an EMF inside it. We want to find expression for that instantaneous EMF which is induced in the coil due to its rotation inside the uniform magnetic field. So for doing that, we will be using the Faraday law of electromagnetic induction, for which we need to first find out the total magnetic flux linked with the coil. Now, when the coil rotates, here you can clearly see that the normal to the surface of the coil, that is the area vector of the coil, is making this angle theta with the direction of the magnetic field. So over here, if we drop a perpendicular from the direction of the magnetic field onto the area vector, then we get this right angle triangle, and in this right angle triangle we can decompose this magnetic field into two rectangular components. Along the normal we will have the component b sine theta which is directed along the coil, and other component which will be b cos theta which is directed normal to the surface of the coil as it is also shown in the figure. Now the magnetic flux linked with the coil, it will be phi equal to phi equal to ba into cos theta. Theta is equal to omega t, so we can write it as ba into cos of omega t. So using Faraday law of electromagnetic induction, the EMF induced the coil will be minus d phi by dt, which will be equal to minus d by dt of ba into cos of omega t. Ba is a constant, cos in differentiation is minus sign, so it will give us minus d by dt, it will give us minus ba into minus sine of omega t into omega. That will give us E is equal to ba into omega into sine of omega t. This is the flux linked with the one coil. If the coil has n number of turns, then EMF induced will be E equal to nba into sine of omega t. N is the number of turns of the coil, B is the magnetic field applied, and A is the area of the coil. All three factors are constant. So, and omega is the constant angular velocity of rotation of coil. All three factors are constant, four factors are constant, so we can write this equation as E is equal to E naught sine omega t. This equation gives us the instantaneous EMF induced in the coil at any time t due to the rotation of the coil. Here E naught is equal to nba A omega, which is the maximum EMF which is induced in the coil. So by substituting the values of omega t at the various positions of the coil, we can find out the EMF induced. So if omega t is equal to 0 degree, then EMF induced in the coil will be 0. If omega t is equal to 90, E will be equal to E naught. If omega t is equal to 180, E will be again 0. If omega t is equal to 270, E will be equal to minus E naught. And if omega t is equal to 360, E will be again equal to 0. So if we plot a graph between voltage EMF and the angle of rotation of the coil, then we get this shape of the graph, which indicates that when the plane of the coil is in the direction normal to the plane of the coil is in the direction of the magnetic field, that is when area vector and magnetic field are parallel to each other, flux is maximum but induced EMF is 0. After 90-degree turn, when no flux pass through the coil, area vector is normal to the direction of the magnetic field. In that case, EMF induced in this case will be maximum at this case. Again, when the flux through the coil becomes maximum, EMF again become equal to 0. So when plane of coil is further rotated by 90 degree, that is it reaches to 70-degree position, EMF becomes reverses its direction, becomes minus E naught, and 360 degree it become again 0. So we get this sine curve, or we can say that EMF induced in the coil is varying sinusoidally with the time, and at any instant of the time the EMF induced in the coil is equal to E naught sine omega t. Next is self-induction. This is a very important topic, self-induction. So what is a self-induction? Self-induction is the phenomena of inducing an EMF in a coil when a changing current is passed through it. So whenever in a coil current is undergoing a change, then EMF will also be induced in the coil, and if the coil happens to be in a closed circuit, then an induced current will also start flowing through it. This we call as the phenomena of self-induction. In order to explain the phenomena, in the figure what we have connected with a coil a battery and a key K. If you keep the key open, no current will flow through the coil, current will be 0, no magnetic field will be produced, so no EMF or current will be induced in the coil. But if you suddenly close the circuit, the current in the circuit will begin to rise. Suppose this battery can make 3 ampere of current to flow through in the circuit. That means when suddenly the circuit will be closed, the current has to rise from 0 to the 3 ampere. So during that small time in which current will be rising from 0 to 3 ampere, that time is known as the transient time. That time is known as the transient time, and the current which is rising now from 0 to 3 ampere, we call that as the transient current, changing current. Due to that, this current when flowing through the coil, it will be producing the magnetic field, and due to continuous increase of the current, magnetic field will also be increasing. So this changing magnetic field, this increasing magnetic field, it will develop an EMF or induce an EMF across the two ends of the coil A and B, due to which, because coil is in closed circuit, an induced current will begin to flow. And as said by the Lenz's law, any EMF or current induced in a coil is always have a direction such that it always tries to oppose the cause of its production. The cause of the production in this case in the coil is increasing current. So you can see that the current supplied by the battery in the coil is flowing in the clockwise direction. So this increasing current is responsible for the induced current, and according to Lenz's law, the current that is induced in the coil, it will try to oppose the cause of its production, which is the increasing current from the battery in the clockwise direction. So in order to oppose this current by the battery running in the clockwise direction, the EMF will set up its polarity at end A and B in such a direction that the induced current will flow opposite to the direction of the current supplied by the battery. So current by the battery is running clockwise. So current that will be induced here in the coil, it will be running in the anti-clockwise direction so that it can oppose the increase of the current by the battery. When the current reaches its 3 ampere, transient condition will disappear, current will begin stop changing, maximum current will be arriving, magnetic field will become constant in the circuit, changing magnetic flux will disappear, so induced current will also disappear. The same thing happens when you suddenly release the circuit. When suddenly the circuit is released, the current in the circuit by the battery now begins to fall. Now it has to move from 3 ampere to 0. Again transient conditions will be arriving. So again decreasing magnetic flux will induce another EMF and another current will be induced inside the coil. But in this case, the induced current will reverse its direction. So in this case, the induced current which was earlier flowing in the anti-clockwise direction, now it will continue to flow in the clockwise direction. Reason, the cause for induced current in this case is the decreasing current. So the EMF or the current that is induced in the coil according to Lenz's law doesn't want this current to decrease, because this is the reason of its production. So in order to stop the current after switching the key open to decrease, the induced current also begins to flow in the clockwise direction so that it is able to maintain the current in the coil as well as the magnetic field. So induced current in this case, it is flowing in the clockwise direction. So in both the cases, when the circuit is suddenly switched on or when it is suddenly switched off, and current is induced in the coil due to an induced EMF. So this phenomena in which current is induced in or EMF is induced in the same coil in which a changing current due to battery or due to some other sources flowing, we call it as the self-induction. Now, if at any instant of time the current flowing through the circuit is I, then the magnetic flux linked with the circuit, it will be directly proportional to the current flowing in through that circuit. So I here is the instantaneous current, phi is the instantaneous magnetic flux. Or we can also write this equation as phi is equal to L into I. Here, this is our first equation. Here L is a constant which we call as the coefficient of self-induction, or we also call it simply as the inductance of the coil. If this is the self-induction, now in first equation, if I is equal to 1, if we put I equal to 1, then from first equation, phi is numerically equal to L. So what is the meaning of the coefficient of self-induction? If we put I equal to 1, that means if the instantaneous current running in the circuit is equal to 1 unit, then phi become equal to L. This means that the coefficient of self-induction is nothing but the instantaneous magnetic flux present in the coil when a unit current was flowing at any instant of time. If we use the law of electromagnetic induction, E is equal to minus d phi by dt, it will be equal to minus d by dt of L into I. L is a constant quantity, so it can be taken outside the differentiation, so it will be minus L into di over dt. This is our main second equation. Here you can clearly see that E is directly proportional to di by dt. That is, EMF induced in the coil is directly proportional to rate of change of current. So greater the rate of change of current, more EMF will be induced. Negative sign, according to Lenz's law, the EMF induced will try to oppose that change in the current. One thing, the coefficient of self-inductance of the coil is a constant factor here. Why it is a constant factor? Because this coefficient of self-inductance depends upon the number of turns of the coil. It depends upon the area of cross section of the coil, and it also depends upon the permeability of the medium which is present in the interior of the coil, whether it is air is there or some kind of magnetic material is there around which the coil is winded. All these three factors will define the coefficient of self inductance of a coil. Now in this equation 2, if we have di over dt is equal to 1 unit, then E is equal to minus L. That is, if di by dt is equal to 1, that means current in the circuit is changing at the rate of unity. Then EMF induced numerically is equal to the self-inductance. That means self-inductance is actually giving us the magnitude of the EMF induced in the coil. Then the current in the coil is changing at the rate of unity. Unit of self-inductance from the second equation, in the scalar form we can write it as L equal to E divided by di over dt. We are skipping the negative sign because it is showing only direction. E is induced EMF, unit 1 volt. Di by dt will have unit 1 ampere per second, which we can write as 1 volt second per ampere, and this is known as 1 Henry after the name of scientist, if we are using symbol capital H. So the self inductance of the coil is 1 Henry if 1 volt of EMF is induced inside it when the current through the coil is changing at the rate of 1 ampere per second. So 1 Henry is the unit of the self inductance of the coil. We can also express 1 Henry as 1 Henry is equal to 1 volt second per ampere, which you can also write it as 1 Weber per ampere. Last, dimensions of the self inductance. We know that L is equal to phi over I. Phi is equal to BA over I, and B can be written as F over QV, because F is equal to QVB sine theta. Sine theta we are neglecting because it is a dimensionless quantity. So the dimensions of self inductance are M1 L1 T minus 2 L2 divided by velocity L1 T minus 1, current A, and Q is the electric charge, which is equal to A into T. So if you solve it, finally we will get equation value M1 L2 T minus 2 into A minus 2. These are the dimensions of the coefficient of self inductance of the coil. Thank you.